So, good morning, everyone. I am Emanuele Arcieri from the University of Bergamo, Italy, and I'm glad to welcome you to this thematic symposium entitled Structural Integrity and Durability of Lightweight Materials and Structures. The focus of the symposium is to discuss the state of the art and the new discoveries on the analytical modeling, numerical modeling and experimental testing of materials, components, structures, and systems, with a focus on some engineering fields such as aerospace engineering, mobility engineering, so vehicle engineering, racing engineering, and also all these fields that required energy efficiency. So I asked to the presenter to present their activity in 10-12 minutes in order to have a few minutes for the discussion. And we can start with the first presentation that is mine. So the title is Structural Integrity Assessment of a Lightweight Bicycle Frame, Finite Element Analysis and Experimental Testing. The authors are Arcieri and Baragetti from the University of Bergamo, Italy. So after the coronavirus pandemic, the European Union gave Italy some funds that constitute the National Recovery and Resilience Plan. This plan has different missions, and one of these is sustainable mobility. In this framework, the National Center on Sustainable Mobility, MOST, was born, which includes more or less industries and university from all the regions of Italy. The aim of this center is the implementation of modern, sustainable, and inclusive solutions in various mobility areas. One of the spokes of this center is focused on light vehicle and active mobility. My university, the University of Bergamo, is the spoke leader. The other university partners are Politecnico of Milano, Università degli Studi di Brescia e Università degli Studi di Firenze. And we have also industrial partners that are Angel for Future for the electric charging infrastructures, Brembo for the brakes, Pirelli for the tires, and Poste Italiane, that is the national service, the national post service. One of the possible vehicles is for Poste Italiane, so for our post service. So the presentation of today is focused on the structural integrity assessment of one bicycle frame provided by a company in the province of Bergamo. The frame is made of titanium, so we have a very, very low weight of the frame. And today I will present only the static assessment of the frame, which is the base for the fatigue assessment according to a national standard and international standard for us. The British standard, the IENA ISO 4210, cycles safety requirements for bicycles, frame and fork test method. According to this standard, we can test the bicycle frame with its real fork or a dummy fork, and we have to apply a cyclic loading with a maximum value of 1,200 newtons in tension and 600 newtons in compression for a defined number of cycles. In this presentation, we focus only on the static loading with a force of 100 to 1,200 newtons in order to validate the finite element created for the fatigue assessment. So a robust research methodology, but also design methodology, includes theoretical approaches, numerical approaches, and experimental approaches. The comparison of the results provided by each of these methodology allow us to reduce the possibility of error because we have different approaches. Actually, in this study, we used the theoretical approaches for the design of the experimental equipment to adequate our tensile testing machine that we have in our laboratory. It is a prototype, and we adequate this machine to test our frame. Then we carried out a finite element analysis on the bicycle frame. We will see two types of finite element analysis, and then experimental testing on the system. So bicycle frame with the dummy fork. So here you can see the systems that we have designed. So we have the rear dummy hub and the dummy fork. As regards to the dummy fork, the standard requires only stiffness. So it is prescribed only a level of stiffness, but we have designed it in order to have a suitable and adequate fatigue strength in order to use it for other tests. Okay, let's start with the first finite element model that is made with beam elements, so 1D elements. We have the frame and the dummy fork with beam elements. The material properties are reported in the slide. The boundary conditions are roller and hinge, and you can see the deformation multiplied by 10 times. We connected the rear pin and the fork to the frame of the bicycle with MPC constraint, so a rigid constraint. As you can see, the most stressed areas are on the horizontal tube and the inclined tube in correspondence of the connection with the vertical tube with the fork. Actually, we have not modeled the weldings, so we have not this part of the study. And if we move a little bit farther, because yes, where we have weldings, we have the perturbation of the stresses, we can see that the inclined tube A is the most stressed element and it is subjected to bending. The horizontal tube B is the second most stressed element. The vertical tube is subjected to compression with low stresses. The rear part of the bicycle frame is subjected to very, very low stresses. Now we move to a model with shell elements in order to model in a more accurate way the bicycle frame. And here we can see the contribution of bending and axial internal actions. And as you can see, the stresses increase a lot. And we also obtain stresses that are higher than the ultimate tensile strength of the material. But if we focus, again, we can see that are concentrated in the weldings area. So maybe a more accurate simulation of this part, modeling of this part will allow us to more accurately catch the stresses. In the legend, you can see a limit of plus minus 350 megapascal in order to have already an estimation of the fatigue strength of the bicycle frame. So we reduced a lot the ultimate tensile strength, and so the critical areas for fatigue are those that are in green. Again, we move a little further from the weldings, and we can see that the inclined tube is again the most stressed element, and it is subjected to bending. Horizontal tube B is the second most stressed element, and vertical tube is subject to compression and low stresses. Now we move to the experimental test. As I told you a few minutes ago, we tested the bicycle frame on a prototype that we have in our lab. It is 6 meter height with a load capacity of 50 tons. And so we measured the stresses using strain gauges. We placed 4 strain gauges on the horizontal tube in order to measure also if there were eventual parasite bending stresses due to visa ligaments during the mounting of the system. 2 strain gauges on the inclined tube and 2 strain gauges on the vertical tube. So we carried out only uniaxial tensile test with a force of 1,200 newtons. We repeated the test 5 times and we measured, as I told you, the stresses with uniaxial strain gauges. If we compare the results of the numerical analysis with the experimental analysis, we can see that the model with shell elements is more accurate to reproduce the stress state in the bicycle frame, even though we have a discrepancy of 20%. However, our model overestimates the stresses, so we are cautious. In conclusion, we had studied the structural integrity of a bicycle frame made of titanium under static loading. We found a good agreement between the numerical results provided by the finite element model with shell elements and experimental results, even though numerical model overestimates the stresses. The future developments on which we are working, actually, are the fatigue strength assessment via numerical model and experimental testing, the identification of suitable geometries. So if we can reduce the thickness of the tubes, for example, or change a little bit the shape of the tubes. And then the study of e-bikes. We are now studying a frame for an e-bike made of aluminum alloy. So thank you for attention.